Now in this part of the lecture we shall solve some problems on DTFS. The first problem says that for a discrete time periodic signal x of n equals to cosine of pi over 3n, where n goes from 0, 1, 2 to n minus 1, where obviously n is the period. We are to determine the spectrum of the signal and the power density spectrum. Now then, let us solve the problem. Here x of n is periodic. Say with a fundamental period being omega naught, which is equal to pi by 3. That means this term. Now from the previous lecture, if you can recollect, omega naught always occurs like this, twice pi over n. So equating these two values, or pi by 3, we get n equal to 6. And the fundamental period consequently becomes omega twice pi over 6. What I have done is multiplied the numerator and denominator by 2, and we got twice pi over 6. This is the required fundamental period through which we will proceed the calculation. Now, in general cases, in order to determine the Fourier series coefficient, we are required, that we require to use the, analysis equation. So, in general cases, we use the analysis equation in order to determine the Fourier series coefficients. Now what does the analysis equation looks like? It looks like C of k equals 1 over n, and taking a running sum which goes from k equals 0 to n minus 1, x of n e to the power minus jk omega naught n. But in case there is a sinusoid as the given function, we shall try and use the synthesis equation in order to solve for the Fourier series coefficients. So let us do so. Here x of n equals cosine of pi over 3n, which can be written as, from the Euler's expression, e to the power j pi by 3n plus e to the power minus j pi by 3 n over 2. This expression comes from, say, e to the power j theta equals to cos theta plus j sin theta, and e to the power minus j theta equal to cos theta minus j sin theta. In order to determine the value of cos theta, let us add both the expressions. This becomes add, this becomes subtract. That means the signs are not changed. This is e to the power j theta plus e to the power minus j theta, twice of cos theta. These two terms cancel each other, and consequently we get cos theta to be equal to 1 over 2 e to the power j theta plus e to the power minus j theta. So we have used this expression for calculating the value of cos pi over 3n. Now if we expand this equation a bit further, we get it to be equal to 1 over 2 e to the power j pi by 3 n plus half e to the power minus j pi by 3n. Now let us compare this equation. Say this be A. Let us compare A with the synthesis equation, where we can write half. Before that, let us write down the synthesis equation, which looks something like this: x of n, where n goes from 0 to n minus 1, c of k, e to the power j kn omega naught. So 1 over 2 remains as it is. We can write e to the power j pi by 3 as twice pi by 6 times 1, and n remains as it is. Comparing these two equations. So let us disregard the summation sign for this time. We get c of k to be equal to 1 by 2. E to the power remains same. J and j remains same. Omega naught becomes twice pi over 6. That is, I have said omega naught here. Twice pi over 6. The value of n is remained as it is. So what is this 1 that we have multiplied? This is the value of k. So by multiplying this 1, we have defined the value of k in this part of the equation. Now moving forward, in the next part we can write similarly half e to the power j twice pi over 6 minus 1 n. Half remains as it is, c of k, and j is similar as well. Omega naught we have written twice pi over 6 here. N remains as it is, and for the value of k we have taken minus 1 for this negative value. So if we compare these two equations, we can easily write down that c of 1 equals half, that is c of k, and here in this part of the expression, let me write it with another color. In this part of the expression, the value of k is 1. So we can write C of 1 to be half, and consequently in this part where the value of k is negative of 1, C of minus 1 to be equal to half as well. Now let us plot the spectrum of these coefficients that we have found out. These are the Fourier series coefficients using which we can plot the spectrum. Now from the previous part we have found out C of 1 to be equal to half and C of negative of 1 to be equal to half as well. So if we plot C of k with respect to k, this being 0, this is the first sample, 1, 2, 3, 4, 5, 6, 7, 8. And this side 1, 2, 3, 4, 5, 6, 7, 8. Let us mark this as 1, 2, 3, 6, 7, 8. This is negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, and negative 8. So, at the point where k equal to 1, we get a value of half. And similarly, at the point negative of 1, we get another value, half. Now remember, the summation for C of k in the analysis equation, which is 1 over n, runs from k equals to 0 to n minus 1. That means after n minus 1, the signal will repeat once again. So what is the value of n? Rather than let us take 1 to n for the ease of calculation. So what have we got? Here we got the value of n to be equal to 6. That means that here n equals to 6. So if we start from 1, so after 6 value in the 7th sample, the signal will repeat once again and this will become half, and consequently this side also the signal will repeat once again. This value becomes half. Now once again if you observe carefully, from minus 1, if we repeat the signal, that means if we go through 6 samples, that is 1, 2, 3, 4, 5, 6, here the signal will be repeated once again. For this sample, this is repeated to half, and consequently for this sample, this is repeated to half. So this is 1, 2, 3, 4, 5, 6. At minus 5 we get. So this is the coefficient, Fourier series coefficient, that is the frequency spectrum that we were required to calculate. Now in order to determine the power density spectrum, for the power density spectrum, we have P of x to be equal to summation of k, which goes from 0 to n minus 1, C of k squared. So basically what we are saying that if we can draw a squared version of this graph, this will give us the power density spectrum of the given function. So let us plot C of k squared. So we get 1, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7. So we get a sample here the value will be 1 over 4, that is 1 over 2 squared. And in the 1, 2, 3, 4, 5, it will also be 1 over 4. In 7, this will also be 1 over 4. In negative of 1, this will be 1 over 4. In the fifth sample, 1, 2, 3, 4, 5, this will be 1 over 4. And consequently, this will also be 1 over 4. So, what have we learned? We have seen that by simply squaring the magnitude spectrum of any given function, we can determine the power density spectrum. Now, ladies and gentlemen, I would like you to recall the property of real and even signal. Now, in this problem, the initial signal was cosine of pi over 3n. So the cosine function goes something like this. Now, if this is the signal, that is a cosine function, we can easily say that the signal is real. Of course it is real, there is no imaginary value in a cosine function, and even, because if we mirror this part over here of the signal in the negative x-axis, we get the same result. So, according to the property of real and even signal, C of k will also be real and even. Look carefully at this signal. What we can see is that if we discard this part for the time being, if the signal is real, of course it is real because all the values are having half, which is undoubtedly a real quantity. If we mirror this part in the negative k axis, we shall get the same results. So if we mirror this part in the negative k axis, we get the same result at the same instance of k. So once again, we were able to verify the property for real and even signal. So I hope you have understood the problem, and let us go to the next problem, in which we shall be doing the same thing for a different signal.